Okay, welcome to chapter 9. We'll be talking about alcohols and epoxides, and I will break this into two lectures. One will do alcohols, and the next one will do epoxides. You do have assigned POGLs for both alcohols and POGLs for epoxides, which really help you think about things and problem solve. So I suggest you work those along with this material in your reading. Okay, so this is obviously from a review slide, and you're trying to decide, we have an alkyl halide, and it is a primary alkyl halide. And so what's our conditions? We have, this would be considered a strong nucleophile, would also be considered a strong base. In this case, since it's a primary alkyl halide and a strong nucleophile, you can assume that this is going to be SN2 that's going to happen the fastest, because the primary alkyl halides react the fastest for an SN2 compared to elimination. And so you see that I drew in the reaction mechanism, which in this case is concerted, so it's happening at the same time. It is backside attack, and those electrons go with the leaving group. And so then if you were to predict your product, you'd have 1, 2, 3 carbons, and then you have OCH3, and then sodium chloride and bromide. But we don't care about that because that's not your major organic product. So we have made an ether. So B is your answer here. And we don't have to worry about stereochemistry because you don't have a stereocenter there. All right, so this chapter is alcohol, ethers, and epoxides. The previous slide we did make an ether. That was a methyl propyl ether. And so methyl propyl ether is something like this. So you see this is a propyl group and this is a methyl group. And the nomenclature is such as that. Alcohol, ether, and epoxides. So this is an alcohol functional group. You have so oxygen, its preferred bonding pattern is 2 lone pairs and 2 covalent bonds. And when you do the preferred bonding pattern, you don't have to worry about formal charges. And so your typical functional groups do not have formal charges. And so you see this alcohol is one where the oxygen is bonded to the carbon and then a hydrogen. Ether, the oxygen is going to be bonded to both carbons. Now, epoxide is a special type of ether. And it is a stringed ring ether. So obviously a triangle has 60-degree bond angles, but this should be a 109.5-degree bond angle because it's sp3 carbon. So it has significant strain with a heteroatom. And so epoxides do exist in nature, and then we are going to see reactions with epoxides. You'll find that ethers are pretty much inert. That means they're not very reactive. So we won't do a lot of reactions with ethers. These typically, for that reason, become your solvents. So solvents enhance a reactivity, but they do not participate in the reaction. So like tetrahydrofuran, which you'll see is THF. This is tetrahydrofuran. That's a common solvent. Diethyl ether. This is diethyl ether. And these would be polar, slightly, weakly polar, but they're also aprotic because they're not like, methanol, which you have a hydrogen next bonded to the oxygen. So that would be protic because it can do hydrogen bonding. These are polar protic. Your ethers are going to be polar aprotic. So those are great solvents for SN2 reactions, correct? Like I said, alcohols are going to be polar protic, and those are also a lot of your solvents. You would never want an epoxide as in a solvent. The reason why is because they're very reactive. They're very reactive. Okay, so an alcohol is an sp3 carbon. So those are 109.5 degree bond angles, and they typically have a dash and a wedge if it's a stereo center on the carbon. Um, these are example of cortisol, which is your anti-inflammatory steroid, and you see that you have 3 alcohol functional groups on that molecule, and you want to classify alcohol. So just like alkyl halides, when you see them, you classify them. And by classify them, you can kind of characterize them and which kind of reactions they're going to undergo. Is that going to be SN2? Is it going to be E2, SN1, or E1? And the classification helps. So where you're going to find the alcohols and classifying alcohols is also going to be helpful. This is a secondary. Why? Because the carbon, it's called the carbonyl carbon. So that's the carbon that's bonded to the OH is bonded to 2 carbons, which makes it secondary. This carbon here, the carbonyl carbon, is bonded to 3, so it's tertiary. This carbon bonded to only 1 carbon is a primary alcohol. Okay, the oxygen hybridization, it is sp3, and it's because the carbon is sp3. You'll find that, like if you have an amide, this is an amide, you'll find that since this carbon is sp2, you'll find that the nitrogen is also sp2. And you might say, why is that? Because, you count the lone pairs, and that's 1 thing, 2, 3, 4, that's 4 groups. Well, the lone pairs, if they can participate in resonance, they will. Okay, and in order to do resonance, you have to have an sp2 or an sp element hybridized. So this can, resonance always wins, remember that, will participate in resonance, and so this is what that looks like there. Okay, so this is the same structure. Remember, that's a thing about resonance, they're the same structure. The only way that those lone pairs can participate in resonance is if it has an unhybridized p orbital. Now, if you look at nitrogen, okay, how many things are bonded? 1, 2, 3, so sp2. So it's an sp2. That's sp2. Now, what about the oxygen? Well, you could say, okay, there's 1, 2, 3, 4. It's sp3, but it's not, because you would look at this resonance structure and say oxygen's sp2. If the element can participate in resonance, it will. How do you know that? Is if the next door neighbor is an sp2, then you decide whether to count that lone pair. If you have to, draw resonance structures if you can. Here, this oxygen is bonded to an sp3 carbon, so we will count those lone pairs as a thing. So that's 1, 2, 3, 4. So that's sp3. And this is an ether. So in epoxides and alcohols and ethers, you have an sp3 carbon. Alcohols and ethers have a bent shape like water. That means the lone pairs are on the same side, and that is bent. Naming, well, okay, so there's priorities. Now that we're getting into more functional groups, certain functional groups have higher priorities than others. And as you come across these functional groups in your learning, the chapters you need to know. And it's based on reactivities. So alcohols have a higher priority than the double bond or triple bond or a halide. So it needs to have the lowest number. So that it tells you, okay, so you still find the longest chain. 1, 2, 3, 4, 5, 6. But now you're going to count from here. 1, 2, 3, 4, 5, 6. Because you want to give the OH the lower numbering. So 6 is hexane, but it's going to be hexane 3-all, and then you have the substituent, which will be 5-methyl. And so this is where the alcohol gets the lower numbering because it has a higher priority. So you want to number the chain that way from left to right. When it's bonded to a ring, it's going to be the higher priority. So you start there, and then to get to the substituent, you want to give it the lowest numbering. So you can either go clockwise or counterclockwise. Here you get to the methyl by going counterclockwise. So that would be how you would name that. So here the second substituent is at a 2. So this is 2,5,5 trimethylcyclohexanol. Common names. Sometimes you see common names, isopropyl alcohol. They're just separated by a space in the functional group. If you see diols, 1,2-diol, triol, 1,2-diol. Notice that this is a ring. You have a wedge above the ring and a dash below, so that's a trans. So the intermolecular forces, for alcohol, it's going to be hydrogen bonding. They're going to have higher melting points and boiling points. Ethers are just, they actually have a very weak dipole-dipole. So this is a hydrogen bonding with the hydrogen here. And do you see that dashed line? What is the name of the major organic product in this reaction? Okay, so what's the product? So first we've got to pick the product, and then we're going to name it. Here is a great leaving group, the tazole, and this is a secondary. So remember, secondary alkyl leaving groups can either go all kinds, SN1, E1, SN2, E2. So you got to look at the nucleophile. The nucleophile is a strong, because I gave it a negative charge, right? Because the sodium's plus, a strong nucleophile. So a strong nucleophile is going to go with a secondary. It's going to go SN2. So this is concerted. We do have stereochemistry, so we do have to show inversion of stereochemistry. Okay, so here's, and if this is going back, this is going to, the nucleophile is going to come from the top, and there's your alcohol. So now we want to name that. We want to find the longest chain, but our naming is going to have to give it the lowest number. So we're going to do that, and you see that that's hex and 3-all, and then we have this here, 4-methyl, but then we also have to do R and S. So we got to assign priorities. So that will be 1. And then what you don't see is the hydrogen going back, which is 4. And then so this is a CH2, this is a CH. So this has, that carbon has a carbon, carbon, carbon. This just has a 1 carbon. So this one gets a 2. And then this would get a 3. So then if we connect the 1, 2, 3, we are turning the steering wheel to the left. So that is an S. And so that's counterclockwise. We're turning it counterclockwise. It's an S. Does S stay S? Yes, because our lowest priority is in the back. So this is 3S. You put that kind of like that in parentheses. 4-methyl hexane 3-all. So that would be your name. Okay, so how do you prepare ethers? You're going to learn that's Williamson ether synthesis. So you'll notice when you're doing these reactions, for each one of these chapters in organic 1 and 2, you are introduced to the functional group. So you're introduced to the functional group, its intermolecular forces, kind of its properties with melting points and boiling points, a little bit of how to name, and then how to synthesize them, how to make them. And so the way you make ethers is Williamson ether synthesis. This is a Williamson ether synthesis. Williamson ether synthesis. And so that's right here. It requires a primary alkyl halide and an alkoxide. And it undergoes an SN2 mechanism. You've already been doing this, folks. It's an SN2, and that makes an ether. Here, if you do sodium hydroxide, the SN2, then you can make an alcohol. So those reactions are not new, but now you understand that this is how you make an ether. Now, why does it need to be a primary? Okay, so we're looking at a primary alkyl halide versus a secondary. Well, if you have a secondary, okay, you would think, well, you could just do this, right? But remember, secondaries with a strong nucleophile, they can also be strong bases. So the problem was you're going to get a significant amount of E2. And so remember E2, there's your alpha, there's your beta. So this is the problem with this, and you'll see this in the POGL. So look for it. This is also a strong base, could go and take this and leave like that. And then you have significant amounts of your elimination product. But if you have the primary, this is going to be super fast. SN2 is fast, 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 because remember it's kinetics. So here, if this is your nucleophile, and then you will only get this ether product. So it does matter. Are you going to break it on this side, or will you break it on that side? And that's called retrosynthesis. This is a retrosynthesis arrow. Retrosynthesis, you'll start seeing, in this case, since this is making the new bond here, the retrosynthesis pathway would be you broke it on that side here. Okay. On this one, since this is the new bond being formed between the oxygen and this carbon, see the red? That is the retrosynthesis. Or you would do the arrow like this, and that's called retrosynthesis. You can Google it. Okay, so an alkoxide salt is needed. So how do you make the alkoxides? You take sodium hydride. Sodium hydride is this white ash. It looks like ashes. Like if something's burned and you have ashes and it's in a can. Okay, and you have to double bag this can. So it's like a metal can. So if you work in a lab, probably won't use sodium hydride in your sodium. This is called sodium hydride. It's a very strong base. You won't work with this in your research or your undergraduate labs unless you do research. But it's like in a paint can. You actually have to get a screwdriver and take the metal lid off, and then it's double bagged, and you put it in a bag and another bag because it's very air sensitive. When I say air sensitive, fire. Okay, you don't want to fire. But anyway, and then it's because it gives off hydrogen gas. When you put this in a solution of alcohol, you start seeing these bubbles, and it's because it's hydrogen gas. So what this is this is an acid-base reaction. And you remember we did an acid-base reaction, your first reaction. So this is your base, and this is your acid. And so anytime you have an acid-base reaction, the base is taking away the proton. You assign pKa's. So this is a 16 on your pK table. And then this is your product. And so where did the H goes? It goes here, right? So these two H's come together to make H to gas. And so that's your conjugate acid. What's the pKa of hydrogen? You'll see that's around 35. So it is like, I don't know, 20 zeros towards the right. So, I mean, if you did 20 zeros and you put a dollar sign, I mean, that's a lot. I mean, 1, 3, 6, 9, 12, 15, 18, 19, 20. So this is happening. This reaction, these products, you put this together, it's pretty much here. Now you've made a sodium ethoxide. Sodium hydroxide or sodium hydride is a great base to make alkoxide. So anytime you're trying to deprotonate a hydrogen from an alcohol, and the reason why is because it generates this hydrogen gas, which is it bubbles out of the reaction, so it's clean. You don't have to, you're not generating any byproducts. Okay, which of the following is the conjugate acid in the acid-base reaction? So here you have the base. So this is the hydride. And here's your acid. So this is your hydrogen that it's going to deprotonate. And those electrons will come and deprotonate that. And then the 2 electrons there will go on to your oxygen. And so what's your product? None of the carbon bonds are affected. The stereochemistry of your oxygen is not affected. And you still have your 2 lone pairs. But now you have these electrons. And sodium's just going to hang out because sodium's positive. It's going to hang out electrostatically with that negative. That makes your alkoxide. And then the hydrogen here is going to bond with the other hydrogen. That's your conjugate acid because that's where, and that's pKa of 35 like we just talked about. And this is going to, pKa of an alcohol is around 16. So it's going to go here. This is your conjugate base, but this is also our major organic product. What's nice is now we can make an ether out of here. I mean, we can go ahead and take this and then we could put in some ethyl bromide, and now you've made an ether there. And that's what you do in organic chemistry. So you can change this alcohol functional group to an ether. And you need to be able to do that. This is Williamson ether synthesis, and this is an acid-base reaction. So what is the following conjugate acid? Well, there's your conjugate acid. That's hydrogen gas. Okay, AOH minus, bad. Let's write the word horrible, leaving group. Horrible, leaving group. Very poor, not leaving. Okay, not leaving. See that? So do not make it a leaving group, folks. Leaving groups, leave. That's a good leaving group. Not leaving. So we have to convert the alcohol to a better leaving group. So now you're going to learn a series of reactions in order to make alcohol into a good leaving group. So one of the ways is to protonate it. So you can do an acid-base reaction. And this is called protonate. You can protonate your alcohol. And so when you react it with a strong acid, so you add acid to your alcohol, this is your base and this is your acid. This is like a negative 10 pKa. Remember, pKa measures the strength of the acid. So the base will get protonated, and now this has a pKa usually around negative 2. I think I might have, some of them are like even positive 1, but that's a weak base. Now that's a good leaving group. So if you protonate the alcohol, you can make it a good leaving group. Okay, what is the major organic product in this reaction? Okay, so para-toluene sulfonic acid, This is like my favorite organic acid. So this is, you've seen the para-toluene, you've seen the sulfonyl group, because you've seen like O-tazole, the tazolate. So this kind of has that, but instead of the oxygen, so O-tazole, this would be a tazole. But when you have a hydrogen there, it's tosic acid. You'll see it like tosic acid. Para-toluene sulfonic acid. Para-toluene sulfonic acid. And I believe this has like maybe a pK of -7, so it's a very strong acid. And you can just put it in organic solvents. That's what's beautiful about it. You don't have to use something like sulfuric acid, HCl. These are water soluble. These are inorganic acids. And you don't want that. It's not very elegant. So here's, this will donate this proton here to make, so this would get a proton. Okay. And then that becomes this molecule here. Now, this is a secondary, and now it's an alkyl halide with a good leaving group. Why is that a good leaving group? Because it makes water, folks. Water is very stable, so water is a good leaving group. So now what does that do? That gives us this molecule here. What is that? That is a secondary carbocation. You don't have a nucleophile. This is no nucleophile. So you don't have a nucleophile in there. And so this is going to be an E1. And so this is secondary, so we got to do the carbocation test. If we trade places with a hydride there, it becomes a primary. Primary is not more stable than secondary. Here we have a methyl. If we traded places with this methyl, and we did a, I don't know why they do this squiggly, but that's significant of a methyl shift. And so the whole methyl group shifts. Then you get a rearrangement. And not only is that a tertiary, but it's also benzylic. So this is a benzylic tertiary carbocation, which is going to be really stable. And so you just see it was that methyl that shifted. This is that carbon there. This is that carbon. And then this is the carbon that's still there. Okay. And now a hydrogen. So that's kind of like your alpha. So this is your beta because we're doing an E1. So we got to make an alkene. The tosic acid can come and take that hydrogen away to make D is your answer. So that's the E1 product if you put an alcohol in strong acid. So this is dehydration. Dehydration makes elimination. So this is going to be an E1. An E1 is your dehydration. So if you use acid, any form of acid, and you dehydrate this, you're going to have a elimination product, and it's going to be at the Zatsevs, because you will have a carbocation anytime in the one, the unimolecular means you're going to have a carbocation intermediate, and so it will always do a rearrangement. Okay, you get always a rearrangement to form a more stable thermodynamic alkene. So tosic acid is one of these. A lot of times you use sulfuric acid. There's your pK, -7, and para-toluene sulfonic acid. And so each one of these, this OH, step 1, and you need to be able to write the mechanism of this, gets protonated and forms the carbocation. Let me just write the carbocation here. 1, 2, 3, 4. That is a tertiary, so that's fine. And that's always going to be your alpha. And then so where's your beta? Drawing your beta hydrogen. And then you can just write, since this is a catalyst, it has to regenerate itself. And so that's how you get your product. Here, this gets protonated, the tosic acid. And then that's going to leave because this is an E1. And so to do your correct mechanism, you need to show the carbocation. Like I said, that's going to be your alpha. And then so your beta here, beta hydrogen would be there to give you an alkene, E1 product. So the rates of dehydration, well, each one of these you're making a carbocation intermediate, E1. So tertiaries are always going to be faster because they're more stable than a secondary. Primaries, yeah, would that even be an E1? Time you protonate that, I think that it would be an E2 in acid conditions. Notice it's going to be slow. Okay, Zatz's rule. When you have, it's Zatz's rule. We've talked about this, and as you can see, you're going to get the major product is going to be your tri-substituted. It's an E1 mechanism, so secondary and tertiary degrees react by E1, primary degrees react by E2. And we just looked at that, and this is the mechanism we have gone through. So make sure you understand that mechanism because you'll need to be able to write that. So first tertiary and secondary degree, E1, this is pretty good. You don't have any byproducts, no competition with SM1. E1 dehydration of alcohols is more synthetically useful than the dehydrogenation of alkyl halides. You still have to deal with carbocation rearrangements. So a lot of times people don't want to deal with carbohydrate rearrangements if it's possible. This is showing you a primary, and this would be an E2 mechanism. As you can see, there's your alpha and there's your beta, and you have 3 curved arrows. So this would be concerted to give you the alkene. Like I said, carbocation rearrangements are not great, and so you're going to get that. So when this gets protonated and leaves, then you get this compound here. Then it goes as a methyl shift, where this will shift there, and then you have your carbocation now is on this carbon because this carbon shifted there, and then your the beta hydrogen will give you that product, and that will be your major product. So I expect your major organic product to be the more stable carbocation rearrangement. This is showing you a 1,2 hydride shift. If this is an H, those electrons go with the hydrogen. An alkyl shift is like a methyl, and so the carbon will take its electrons, and then that's just what that does is it trades places, and it can only be next door. This is showing you what that shift looks like, so you can see that this carbon is now doing an alkyl shift. This would be an alkyl because it's taken the carbon. Alkyl. Sometimes I just call it a methyl shift. 1,2 shift, and then there's your carbocation. It's going to be more stable. Those tertiary carbocations are more stable than secondary, and more stable than primary. Also in here is allylic. So if you remember, that would be allylic, and then benzylic, benzylic. And the reason why those are more stable is because of resonance. So you can imagine these electrons here can go there, and you get this resonance structure. This is just showing you, this is done, this E1 dehydration of alcohols are done in catalytic amounts of acid to make the OH, to convert OH to a good leaving group. That's OH2, so good leaving group. To do that, it's catalytic, so then this will be regenerate your catalyst by deprotonating that beta hydrogen. And it shows you're going to get the thermodynamically more. Here you have a tertiary carbocation. You have no rearrangement will occur if it already is in a tertiary carbocation, because that's going to be your more stable. Now, another way you can do it, then this is going to be an E2 mechanism. You can convert, in this case, the oxygen OH is converted to a to like a phosphate leaving group. So phosphorus has an expanded octet because it has d orbitals, so it can have 5 bonds. What this does here is this comes up, leaves, this leaves a mechanism that you'll learn in organic 2. But what you need to know is this oxygen now is bonded to the phosphorus, and this is your intermediate. So you make this intermediate. Typically you add pyridine. So this is your alpha carbon, and this is a secondary. So then this is your beta, and you add pyridine. This pyridine will go and take this hydrogen, and this will be a leaving group, and that's how you make your cyclohexene. The reason why this is nice, you have no carbocation rearrangement. You don't have to worry about that in an E2. So it converts a poor OH leaving group into a good leaving group, and this is the leaving group. You've seen these phosphoryl compounds in DNA. You might not have thought about it, but your phosphodiester backbone contains great leaving groups, folks. Dehydration proceeds through an E2 mechanism. So if you're going to use POCl3 and pyridine, you're going to have an E2 mechanism, and you're going to have no rearrangements because you don't have to worry about rearrangements, right? It's an E2. It's concerted. So, but here you're just converting the oxygen into the OH into a great leaving group, and then this is your concerted elimination reaction. Another way is to convert the OH into a different functional group. So this is just showing you once again, you take this and you react it with some kind of sodium chloride, right? And that's not going to happen. It does not occur. So one way you can convert the alcohol a different functional group. So here, what's happening here, this is an HBr, this is acid, right? So this gets protonated, and now you make OH a good leaving group. So you're adding acid, but I added one too many hydrogen here. But when you do that, you're also, in this case, you have a great nucleophile. So what can happen is this is a primary alkyl leaving group. This can come in and do an SN2. And that's how you can convert that now to a primary alkyl halide. And you know that that's a good leaving group. Here, this is a tertiary alcohol. So what happens is it's going to get protonated. Alcohol will get protonated. Okay, so it's protonated. So now it's a good leaving group. And since that's tertiary, it's just going to leave because it's got a good leaving group. In this case, then you got the chloride has been generated, and that's a good nucleophile. So that's just going to come in. That's not a base, not a base. So you don't have to, no worries for E1. No worries, because not a base, it's a nucleophile, and that's going to come in, and that's going to be an SN1, and this is an SN2. So here's an example of what we just talked about. You protonate, so HCl, HI, HBr. These are they're strong acids, so they can protonate the OH to make the OH, and they protonate it to make it a good leaving group. That's the first thing that happens. And then with the chloride or the iodide, the bromide, you've got great nucleophiles. So you do a proton transfer to make a good leaving group, and now you also generate a good nucleophile, so you can do SN1, SN2, depending on what's your classification of carbon. And so this is showing you that this would be, obviously that's a primary alkyl leaving group, so this would be an SN2 reaction. Here they're showing you that you have a tertiary alcohol, and this is a tertiary alkyl leaving group, and so it's going to leave. This is going to be stepwise. You leave, you can generate your carbocation, and this is going to be an SN1 mechanism because the bromide that's generated in situ, that's when it's generated in the reaction flask in situ, can then make a bond to that carbocation, and that's an SN1 mechanism. So the reactivity towards the O alcohol, this is a stronger acid, and it's a better nucleophile. So HI is going to be the fastest. HCl will be the least because of the size of the chloride. Chloride is not as polarizable as the big iodide, and that's also the reason why it's not as acidic as HI. What is the major product, organic product of the reaction below? Okay, well, this, hopefully you recognize these reagents as an E2 mechanism. This is the Lewis structure of this reagent. Remember that these Lewis structures are the way you solve and work out your organic compounds. This is going to do, and you don't know this mechanism. This is a up and then that leaves. Don't need to know that part, but you do need to be able to make this molecule here. OP, Cl, Cl. So this is the intermediate. And now pyridine. Pyridine is this molecule here. It's a good base. So it likes to go after a proton. So if this is your alpha, and then your beta, there's no beta there. This is your beta. So this is going to come and take that. This is going to be a concerted E2 mechanism to generate this product. Now keep in mind, the reason why this is good and you'd want an E2 is because obviously you want your least substituted alkene. something that's not very thermodynamically stable. The major organic product in pyridine, this is an intermediate in that reaction. Excuse me. Okay, so there are other ways to do we call this a functional group transformation. There's other ways to convert the functional group alcohol into alkyl halides. And so we're going to learn those reagents and mechanism. Okay, so primary alcohols react with SN2 by an inversion of stereochemistry for primary. Secondaries and tertiary react by SN1. So you can get racemization. And the reason why you get that, right, is because you have the carbocation intermediate. So if this is an SN1 mechanism, you get a carbocation, and the carbocation is an sp2 carbon, which is planar and flat. So your nucleophile is going to come in at the top and at the bottom. And so you can convert alcohols into tosylate, which we've seen before. And then how do you do that? You use tosyl chloride. You can see it like that. That is your tosylate here, and that's tosyl chloride. You can react that with pyridine, and it's a way to make a tosylate, so you can convert the OH to a tosylate. And that is I would not say good, I would say that is a great leaving group. You don't have to draw that whole structure. Anytime you want to do that, you can just do like this, O-tosyl. And you need to know that that's what that is. That's a great leaving group. So if you have a nucleophile and you have an O-tosyl, then you can just do an SN2 reaction, such as that. So this is showing you tosyl chloride. It's a nice white solid that you can get in a bottle. You would just scoop some of that in there with some pyridine. Pyridine is a solvent that smells like fish. And that's how you can make your tosylate. Now, this is showing you if you're going to take this alcohol and you're going to make a derivative, you can derivatize it, making an RO-tosyl. This is, the stereochemistry has not changed here. This is your stereocenter, but you're doing reactions on the oxygen, you see. So the oxygen is becoming the O-tosyl. So when you do this, so you might see it something like this. Okay, so let's do tosyl chloride and pyridine. And then let's do sodium bromide. Okay, well, the first reaction, step one, what does that look like? Well, let's do this like this. O-tosyl, or OH. So let's say this is an OH. Okay, so this become O-tosyl. You see how you're derivatizing the oxygen here to make a new bond. That's not a stereocenter. You have not touched your stereocenter there. Now, in step number 2 with sodium bromide, now you have done an inversion of stereochemistry. So that would be the time to do the inversion. So whenever you do substitution or elimination of tosylates, you need to think about the mechanism here. This is a strong nucleophile and this is a primary tosylate. So that's going to be an SN2. And so you see that SN2 substitution, and you make an ether. This is the Williamson ether synthesis. Here, we do not have, this is a non-nucleophile. So it's a strong base, but it's not a nucleophile. So even though you have a primary alkyl leaving group, um, because you don't have a nucleophile, but you have a strong base, you're going to get an E2. You get SN2 inversion when you replace the tosylate, because all of this is a great leaving group. And so here you have a secondary alkyl halide, and now this is coming in, anti-periplanar, and this gives an inversion of stereochemistry, and you can also check out R and S. So overall, inversion of stereochemistry, no different. This is for an SN2 reaction. If I have this here, I'm going to have to draw my chair, and I'm going to put my OH on the axial position above. So we got 1, 2, 3, 1, 2, 3, and the methyl is going to also be above. And so if you were to react that with tosyl chloride, then this becomes your tosyl group, which is a great leaving group because OH is a bad leaving group. So you got to make a derivative. You got to derivatize it with tosyl chloride and pyridine. So now you have this, and now you can take your nucleophile. So this is a good nucleophile, and it's going to come in, and this leaves. And so what does that look like? I'm going to draw it over here. You see your methyl stays there, hasn't been touched, and now your OH, this becomes H, this is going to become OCH3. So you see, if you were to draw that, you get inversion of stereochemistry. It goes trans. This is cis. Okay, so which reaction sequence would accomplish this transformation? This is obviously going to be elimination. Why? Because your product is an alkene. So this is some form. Is it E1 or is it E2? I don't know. I don't know yet. I have to look at things. This is an alcohol. I know that alcohols or OHs are horrible, bad leaving groups. And I see that's a secondary. And so I'm thinking it's not going to be an E1. Now I can see why. An E1 product will always be Zatsev's. So if you do convert this into a good leaving group, that's your alpha, which is secondary. So where are your betas? This is a beta hydrogen, and this is a beta hydrogen. Well, the beta hydrogen, after you get a carbocation, let's say you get a carbocation from an E1. Okay, so there's your carbocation. Well, it's going to rearrange. You will get your most thermodynamically stable product for an E1, which would be this. And look, we didn't get that. So this is going to have to proceed by an E2. So I've got to think of E2 conditions. So it's not going to be acid and heat. It's not going to, this would be E1, and there's no leaving group. So that would really be no reaction because methanol, you don't have a leaving group. This makes tosyl chloride and pyridine. This is tosyl chloride and pyridine. This here doesn't work because there's no leaving group. So let's look at these two. Both of these make this intermediate. So step one is going to make this intermediate. So that's step number one. So now we have a good leaving group. The problem with these options, we don't have a leaving group, so you don't have no reaction. No reaction. All right, now we have the different bases. And believe it or not, any one of these bases would work. What this one, So this is a sterically hindered base, LDA. I don't know if we really went into this. Lithium diisopropyl, lithium diisopropyl amide. So this is sterically hindered. So here's your alpha. And so you have a beta hydrogen here, and you have a beta hydrogen here. If it's sterically hindered, it's going to take, this is called a Hoffman base, and it's going to take the hydrogen that's least hindered. So B is going to give you this elimination product. Sodium ethoxide will take, it's a Zatsev's base, so it's going to give you, it's going to take, let's call this beta A. It's going to take the beta A. This one's going to take the beta B to give you that product, which is what you want. And that would be B. Here you're going to get, well, you're going to get the Zatsev's alkene, and that's not what you want. So B's your. Okay, so the reactivity of hydrogen halides increases with increasing acidity. We discussed this. Ways to convert your alcohol into alkyl halides. And you need to know these reagents and mechanisms. So primary and secondary degree alcohols can be converted to alkyl halides using this is thionyl chloride. Thionyl chloride. Or, and that's going to, or you can use PBr3, which is phosphorus tribromide. And that's going to replace the OH with a Br. And thionyl chloride is going to replace the OH with a Cl. So looking at these reactions, whenever you have a primary or secondary degree and you put it with thionyl chloride and pyridine. Pyridine is just what they call a proton sponge. Keeps it from getting acidic. Thionyl chloride is like this compound here. And so what happens is the alcohol will become derivatized, just like what we saw with the POCl3. So this becomes this compound here. But this also, when this Cl minus leaves, it becomes your in situ nucleophile. And so then it does an SN2, and you get the replacement of the OH functional group with a chloride. Same thing here. SN2 reaction. This is showing you that mechanism that I just showed you. The pyridine just basically deprotonates that, and the chloride will do an SN2 attack. PBr3 does the same thing. It derivatizes the OH to OPBr3, but it's really Br2. And then you also have H here. Now what happens then is the Br minus will come in and that leaves. So this also is an SN2 reaction where the PBr3 transforms the OH into this intermediate compound that also has the in situ nucleophile. So it converts the OH into this intermediate great leaving group and also has the nucleophile. And this is showing you that the OH attacks the Br, and then the Br minus turns around and does an SN2, where this becomes your leaving group to make now an alkyl halide. And so these are the different reagents. If you want to just go straight from an alcohol to an alkyl chloride, you can do HCl. there's some good things, but you also have to deal with rearrangements for um, tertiary substrates. This one is good for primary and secondary alcohols. To convert it to an alkyl bromide, you can use the acid. A better way to do it, if you can, for primary and secondaries is the PBr3. And then there's no other reagent to convert an alcohol to an alkyl iodide without using HI. And this is an example of taking cyclohexanol, and converting. You can make it elimination. This is an E1 product. This is an E2 product that makes an alkene. Here, if you want to convert it to um, a different halide, you can do that. If you take a base, you can also do elimination. Another way we talked about is making a tosylate, and then you can either do SN2 or E2. And that wraps up the alcohol portion for this chapter.